Welcome to the Discrete Universe podcast. Today, we are diving deep into something sent in by you, our listener, a fascinating collection of articles and research notes proposing a genuinely new fundamental theory of physics. It's called Quantum Geometry Dynamics, or QGD.
And our mission in this deep dive is, well, to unpack this material, we're going to explore the core ideas of QGD, looking particularly at its axiomatic foundation.
Yeah.
You know, how it claims to derive the laws of physics.
Right, and how it describes dynamic systems, which sounds really different.
Exactly. And crucially, how all of these concepts compare to the physics frameworks we, especially, with a background in physics, are more familiar with.
Exactly. Knowing you have that physics education, we can really get into the weeds and explore the comparisons at a deeper level. But be warned, this theory takes a pretty radical stance.
So yeah.
The sources suggest it challenges pretty much everything we currently think we know about the fundamental nature of space, time, and matter.
It's certainly not trying to convince you of a new dogma, though. As one of the quotes in the sources puts it, it's really about giving something to think about.
I like that.
It asks you to open your mind to a potentially entirely different way of looking at the universe. Hilbert's sixth problem and the need for a new foundation.
Okay, so to understand why someone might propose something so radical, let's maybe start with some history. Back in 1900, the great mathematician David Hilbert laid out his famous list of problems challenging the mathematical world. Problem number 6 was specific to physics.
Right, building that rigorous axiomatic foundation for the physical sciences, kind of like Euclid did for geometry.
Yeah. Hilbert saw the success Boltzmann had, bridging microscopic physics and macroscopic thermodynamics, but he felt physics needed a more formal, almost undeniable mathematical bedrock.
Like a set of fundamental truths from which everything else could be logically derived. Ensure consistency, completeness, that sort of thing.
And here we are, over a century later, and that challenge feels, well, more pressing than ever, doesn't it? The dream of a unified theory, bringing together general relativity for the big stuff and quantum theory for the small stuff, it seems to have hit a wall.
That's precisely the argument the sources make. They contend the fundamental impasse isn't just technical, it's axiomatic. Like the foundational starting points, the axioms of quantum mechanics and general relativity, they argue they're inherently mutually exclusive.
Mutually exclusive. So you literally can't have both sets of axioms be true in the same system.
That's the claim, which makes a true mathematical unification, one that starts from shared fundamental principles, pretty much impossible without basically throwing out key axioms from theories that we know work incredibly well at their respective scales.
You can't just ignore GR or QM. You need both.
Right. You need both to describe reality. So the sources are saying you can't just bolt them together or tweak them slightly because their foundations are just incompatible.
Okay, and this brings us to Daniel Burnstein's Quantum-Geometry Dynamics, QGD. This recent revision, February 2025, it's presented as a direct response to Hilbert's challenge. It's taking that axiomatic path right from the beginning.
Yeah, you get that sense reading the paper. He includes that quote from Bernard Werber, "What matters is not to convince, but to give something to think about." It feels like an invitation, really.
I like that framing. Here's a possibility, consider it. Not believe this now.
Yeah, exactly. And he also references Max Planck's idea, the one. The new scientific truths sometimes win out not by convincing opponents, but because, well...
The opponents eventually die out, and a new generation grows up used to the new ideas.
Kind of, yeah. It hints that a theory this different might face significant pushback initially.
Given how fundamental the claims are, that seems almost inevitable. QGD's axiomatic approach versus empirical methods.
So most of science, and physics especially lately, has followed what you call an empirical approach. We observe things, run experiments, collect data.
And then build models and laws to fit that data, right? Work backward from the evidence to the rules.
Exactly. You're sort of reverse engineering reality. QGD flips that completely on its head.
How so?
It takes the axiomatic approach Hilbert was talking about.
Yeah.
It doesn't start with the empirical data to figure out the rules. It starts with what it argues are the most fundamental, undeniable aspects of reality, like the basic givens, and it represents those as axioms.
Okay, so what are these fundamental givens, according to QGD?
It boils down to two things that the sources claim all physics theories agree on: the existence of space and the existence of matter. That's the starting point.
Just those two. Space and matter exist.
That's the core idea for the foundation. The entire theoretical framework, including all the laws of physics, is then rigorously derived forward from this minimal axiom set.
So the laws aren't like definitions we invent to match experiments. They're presented as unavoidable mathematical consequences of just accepting that space and matter exist in the way QGD defines them.
That's the key distinction, yeah. The goal is to establish the simplest possible axiom set, describing a dynamic system based on those fundamentals. The theory is built deductively from there. Confirmation only comes later, when the predictions derived from this whole framework are actually tested against observations.
So if the predictions match reality, it validates the starting axioms.
That's the idea. Agreement supports the axioms, rather than the axioms being chosen to fit the agreement.
Wow. Okay, that is a monumentally bold claim. The sources state that from this minimal set, QGD proposes a theory can be developed that describes and explains all physical phenomena, agrees with the predictions of quantum mechanics and general relativity, and is in complete agreement with physical reality.
It's essentially claiming to be a fundamental reboot, deriving the entire physical universe, all its laws, from just a couple of basic assumptions about existence itself. It fundamentally changes how you even think about laws of physics. They're not definitions or empirical fits anymore. They're necessary consequences, core QGD concepts, a different picture of reality.
Okay, so if the laws are derived from these axioms about space and matter, what kind of picture of reality does that force upon us? Because it sounds like it breaks dramatically from the usual continuous space-time framework we're used to.
It absolutely does. Let's start with space and its relationship to math. A core QGD idea is that space is fundamentally discrete, not continuous.
Discrete, like pixels on a screen, but physical, a grid.
Sort of, yeah. Think of it as being composed of individual fundamental units. The sources call them preons. It's a granular structure, a dynamic lattice, maybe?
Okay, so not a smooth fabric.
Right. And the huge implication QGD draws from this is that continuous mathematics, like calculus,
Yeah.
well, it's incredibly useful as an approximation for big stuff, macroscopic scales.
But it's fundamentally wrong at the bottom level.
Inadequate at the fundamental discrete level is how the source puts it. Concepts like mathematical infinity, the continuum, QGD views them as mathematical idealizations that do not physically exist.
Whoa, okay, hold on. Math itself is limited by physical reality being discrete. That's a massive philosophical point, not just physics.
It really is. This view implies a universe that is fundamentally finite and countable, which, interestingly, also means it precludes singularities, those points of infinite density or curvature you get in continuous theories like GR.
No singularities. And
Yeah.
finite, that's
Yeah.
different. What about things like Gödel's incompleteness theorems? Don't they apply?
QGD argues they don't preclude a complete and consistent physics within its framework, because Gödel's theorems apply to formal systems that can encode infinite arithmetic, and QGD is saying its underlying mathematical structure, based on discrete reality, is fundamentally finite. So it sidesteps Gödel, essentially.
Okay. That's a very deep rabbit hole involving logic and math. What about matter in this discrete finite universe?
The fundamental particles of matter are called preons, plus, corresponding to the preons of space. And here's another major departure from the standard model. Axiom 4. It states that these fundamental quantum geometrical particles, both preons and preons plus, never decay or transmute into other types of particles.
Never decay at all, but particle decay is central to the standard model. Protons might be stable, but neutrons decay, muons decay, lots of things decay.
According to this axiom, the fundamental building blocks, the preons plus, that make up matter, are absolutely stable. Their total number in the universe is fixed and finite.
Fixed and finite, okay. So how does mass work then, if it's not about interactions with Higgs field or binding energy?
It's defined incredibly simply. Mass in QGD is just the number of preons plus an object contains. Literally, you count the fundamental matter particles.
Mass is a count, an integer count. That feels almost too simple compared to Ethian or QCD binding energy contributions.
It's certainly different. Now, time. This is the one that really makes my brain bend when I read the sources.
Mine too. Go on.
QGD proposes that time is not physical. It's not a dimension like space. The claim is that reality can be fully described without ever referring to time.
Okay, how? How do you describe motion? Change, cause and effect. How does energy work? Momentum, velocity, if there's no time.
Yeah, that's the hurdle. The answer lies in the concept of intrinsic properties. QGD argues that because time isn't physical, properties we usually think of as depending on time, like mass, energy, momentum, velocity, are actually fundamentally intrinsic to the object itself.
Intrinsic, meaning they just have them, regardless of time.
Yes, and they can be described without the concept of time, A major consequence of this is they are claimed to be observer-independent.
Observer independent. Wait, even velocity. Doesn't special relativity tell us velocity is always relative to the observer?
It does. This is a radical departure, directly stemming from kicking time out of the fundamental physical picture. Velocity, or what QG calls intrinsic speed, is defined differently. It's the ratio of the object's intrinsic momentum vector over its intrinsic mass, the eqpm.
P over m. Okay, so it's based purely on these intrinsic properties. It's not dependent on time or distance in the usual sense.
Exactly. It's not about distance covered per unit time. It's a fundamental ratio inherent to the particle state, its preonic composition and momentum.
So how does the speed of light, c, fit into this? Its constancy is a cornerstone of modern physics.
In QGD, the constancy of c isn't an axiom itself, but emerges as a direct consequence of the discrete structure of space, the preon lattice, and the fundamental intrinsic speed of the preons plus that make up matter. Photons are also composed of preons plus, so their intrinsic velocity is this fundamental speed, c.
So c is like the natural speed limit set by the preons themselves.
Yes, and QGD explains why nothing can move faster than c based on the momentum properties of these constituent preons plus. Intriguingly, it also outlines a procedure to measure the one-way speed of light, and it predicts this one-way speed might not be constant c.
Whoa, really? While the two-way speed, like in Michelson-Morley, would still average to c.
That's the prediction. It's a potentially testable difference from standard assumptions, where the one-way speed is usually just taken to be c by convention. QGD description of dynamic systems. Instantaneous interactions and discrete changes.
Okay, so we've got this picture. Discrete space, no physical time, intrinsic properties, preons that don't decay. How does anything happen? How do things move, interact, change? This must be totally different from describing dynamics using continuous space and time, like, standard Newtonian mechanics or the more advanced calculus-based stuff like Lagrangians or Hamiltonians that underpin so much physics.
It's a complete paradigm shift.
Yeah.
Absolutely. Instead of thinking about continuous motion and forces acting over time, QGD describes dynamics based on discrete changes in position and instantaneous interactions.
Instantaneous interactions. Okay, that sounds a bit like old-school Newtonian gravity, the spooky action at a distance part, before we had space-time curvature.
There's a superficial similarity in the instantaneous aspect, maybe. But the mechanism QGD proposes is derived very differently from its axioms. It describes gravity not as transferring momentum fundamentally, but as changing the direction of the momentum vectors of an object's constituent preons, plus.
So gravity doesn't push or pull in terms of speed, it just steers the preons.
Sort of, yes. The change in direction is proportional to the change in what QGD calls the gravity effect, which is handled by a mathematical tool called the directional vector sum operator plus. Critically, this process preserves the fundamental magnitude of the preon plus momentum, which relates back to why their intrinsic speed remains c.
So gravity bends the path of the fundamental particles, but doesn't change their fundamental speed, c. Okay.
Exactly. And this highlights a key difference the sources point out compared to standard dynamics. Think about Newtonian gravity. The law itself, F n e arrow, calculates an instantaneous force based on positions. But then Newtonian mechanics calculates the effect of that force acceleration as a change in velocity over time.
Ah, I see. So the effect becomes time-dependent, even if the force law itself wasn't.
QGD argues precisely that. It says standard mechanics introduces delays on the action into the dynamics that does not exist in the instantaneous nature of gravity itself, even according to Newton's own gravity law.
Okay, that's subtle but important. So the QGD equation for gravitational dynamics, it says the change in momentum is proportional to g mass. It's different because it avoids that time dependency in the effect of gravity. It's about instantaneous changes in momentum direction tied directly to discrete changes in position.
That's the core idea. It removes the time parameter from the description of how gravitational influence propagates and how it affects motion at the fundamental level. This is a fundamental departure from deriving dynamics by defining force and relating it to acceleration via time.
Okay, so how does this scale up? What about complex systems, like planets orbiting a star or galaxies interacting? How does QGD handle n-body problems without integrating over time?
It uses something called a state matrix to describe the system. The whole system evolves from one discrete state to the next. A state change happens when, say, a reference body moves a tiny discrete distance, maybe just one fundamental preonic leap.
And then what?
Then, for all bodies in the system, the change in their momentum vectors is calculated simultaneously, based purely on the variation in the gravitational interaction resulting from their new positions relative to all other bodies in that single discrete step.
Simultaneously for everything,
Yeah.
based on instantaneous influence.
Which-
That's computationally very different from integrating differential equations step by step over time.
It is. And interestingly, the sources claim that from this approach, instantaneous discrete interactions, QGD, actually drives the first law of motion.
Newton's first law, an object at rest stays at rest, etc.
Yeah, it emerges as a consequence. Interaction with oneself yields zero net change in momentum unless other bodies are present and influencing it. It's not put in as an axiom or an independent law. It's supposedly derived from the interaction rules.
Wow, okay, what about non-gravitational stuff? Collisions, electromagnetism, how are those handled without time, and is momentum transferred there?
Yes, momentum is transferred in non-gravitational interactions. These involve the actual exchange or absorption of particles, or rather preons. QGD provides specific derived laws for these momentum transfers.
Derived laws again, not defined.
Right. They describe changes in momentum following a rule like P equals Ekesmar rho, where X is an integer suggesting discrete packets of momentum transfer, and Keys rho is a constant related to the fundamental preonic momentum. Importantly, momentum is conserved in these non-gravitational interactions.
And Newton's third law, equal and opposite reaction.
That's presented as a direct consequence of QGD's collision laws. The momentum lost by one object in a collision is precisely the momentum imparted to the other, again derived, not assumed.
So even Newton's first and third laws are claimed to be emergent properties in QGD, derived from the basic axioms about space, matter, preons, and their instantaneous interactions.
That's the claim. It's a very different structure compared to frameworks where Newton's laws are foundational definitions or empirical summaries relating force, mass, and acceleration over time.
Does this whole discrete, instantaneous picture apply down at the quantum level too, like inside atoms?
Yes, QGD applies these same derived laws to describe, for example, atomic electrons. A ground state electron is seen as being in an equilibrium state due to what QGD calls extrinsic forces, gravity, and the electromagnetic effect.
Okay. And transitions, like absorbing a photon.
That happens only if the incoming photon's momentum causes a permitted change in momentum, according to that P equals Ekesmar law. It has to be one of those specific discrete amounts. This implies that only discrete momentum states are stable or allowed.
Ah, so you get discrete states, similar in effect to quantum mechanical energy levels, but the reason is totally different. It's about allowed discrete momentum transfers between preons, not wave functions, and quantization rules.
Exactly. Same result, potentially, but derived from a fundamentally different underlying mechanism rooted in discrete space and instantaneous interactions. QGD's explanations and predictions, challenging the status quo.
Okay, this is a lot. QGD offers this radically different foundation. It derives its laws differently. But the big test, right? For any new theory, especially one this ambitious, it needs to match what we already know works and needs to make new testable predictions. Does it reproduce the successes of standard physics? Where does it predict something different?
Right, that's crucial. QGD claims to reproduce the successes, meaning its derived principles lead to predictions that are consistent with observations. But often, the why behind those predictions is completely different from the standard explanation. And yes, it definitely makes numerous distinct testable predictions.
Okay, let's hear some. What about gravity again? You mentioned instantaneous interactions. How does that play out on cosmic scales?
QGD predicts gravity can be both attractive, what it calls peak gravity, and repulsive, angravity. And here's a huge one. It claims that at very large scales, beyond a certain distance threshold they called lambda, gravity actually becomes repulsive.
Repulsive gravity, like anti-gravity.
Yeah, and it supposedly increases proportionally to the square of the distance at those scales. This large-scale repulsion is presented as the explanation for the observed cosmic acceleration, the thing we usually attribute to dark energy.
So QGD claims to explain dark energy via repulsive gravity derived from its axioms.
That's the proposal. And at the other end, at very short nuclear scales, it predicts gravity is significantly stronger and attractive, strong enough to overcome electromagnetic repulsion and bind nucleons together. It also derives the weak equivalence principle.
Okay, repulsive gravity is a massive prediction. What about gravitational waves? LIGO-Virgo's detection was a huge confirmation for GR.
QGD precludes the existence of gravitational waves as described by general relativity, those ripples in spacetime itself. It doesn't predict spacetime ripples.
So, What did LIGO detect, according to QGD?
It interprets those signals not as space-time waves, but as preonic waves. These are described as variations in a polarized field of preons caused by the motion of massive objects like merging black holes. These waves are made of actual preons, plus moving at speed c.
Preonic waves, not space-time waves. Is there a way to tell the difference?
QGD makes a key testable prediction here. These preonic waves could impart momentum to detectors, meaning the detector itself, like the mirrors in LEGO, could experience a tiny physical push or pull from these waves. That's fundamentally different from GR's picture of the space between the mirrors stretching and compressing.
Ah, so it's about how the wave interacts with the detector. That's a potential discriminator. The sources mentioned GW170872.
Yeah, the neutron-star merger with the electromagnetic signal. QGD notes that observation is consistent with its interpretation, potentially involving electromagnetic phenomena alongside the preonic wave.
Okay, so the signal might look similar, but the underlying physics and the detector interaction are proposed to be totally different. What about light? You said QGD sees it as purely particles, corpuscles. How does it explain wave-like things like interference or redshift?
Light is singularly corpuscular, yes, made of preons, plus. Its apparent wave-like behavior, like in a double-slit experiment, isn't due to inherent wave nature, but is explained by the derived laws governing discrete interactions between the light preons and the matter of the slit's specific reflection angles, scattering patterns following momentum transfer laws.
So interference patterns emerge from particle interactions, not wave superposition.
That's the idea. And cosmic redshift. QGD interprets it primarily as a result of these discrete interactions of light preons with intervening preons over vast cosmic distances. It's an alternative mechanism to the standard Doppler effect, based on waves stretching as space expands.
It's an interaction effect, not a stretching of space effect.
Primarily, yes. But QGD also predicts additional intrinsic redshift effects. These happen intrinsically at the source, due to mechanisms within QGD that are distinct from GR's gravitational redshift, though possibly yielding similar results near massive objects.
So the redshift we observe could be a mix of things. Standard motion-related Doppler plus this QGD interaction redshift plus QGD intrinsic redshift.
According to QGD, yes. Observed redshift would be a compound effect. This could significantly mess with our distance and expansion rate estimates if we're only assuming Doppler expansion redshift. Distinguishing these effects observationally would be key.
Okay, how does QGD do on other classic GR tests, like bending of starlight by the sun or Mercury's orbit precession?
For light bending, QGD predicts the deflection angle is exactly twice the angle predicted by simple Newtonian gravity arguments that include a time delay effect. This matches the GR prediction and observations.
Okay, same number, different reason, presumably. Mercury.
For Mercury's perihelion precession, QGD claims its calculation correctly accounts for the observed anomaly. The key difference is how it calculates the dynamics by removing those time delays that it argues Newtonian mechanics, not the gravity law itself, introduces when calculating acceleration over time. It's about getting the dynamics right from its fundamental principles, not adding extra terms.
Reproducing quantitative successes, but deriving them differently. What about black holes? Do they exist in QGD? Are they singularities?
QGD predicts they exist, but as extremely dense, but not infinitely so. No singularities. There are places where matter is broken down into its constituent preons. Plus,
What else?
they're predicted to form intensely polarized jets of these preons, plus, along their magnetic axis. These jets can repulse other matter and potentially explain galaxy shapes. Information about the original matter falling in is lost, which is consistent within QGD's framework.
Any observable predictions?
A key one. The emissions from these QGD black holes, primarily preons, plus, and maybe neutrinos, would be invisible to our current instruments. This contrasts with predictions like Hawking radiation, which should be detectable electromagnetic radiation.
Invisible emissions. That's testable, in principle. What about cosmology? Those recent challenges to the standard lambda CDM model galaxies forming too early hints dark energy isn't constant, tensions and parameters like S8.
QGD claims its framework offers explanations. For example, accelerated formation of early massive galaxies might be due to higher local preon plus density or conversion rates in the early universe. Hints of evolving dark energy could relate to its large-scale repulsive gravity mechanism. It suggests consistency with the S8 parameter tension and offers explanations for things like early ordered galaxy shapes or peculiarities like Andromeda's satellite system.
So it's positioning itself as potentially resolving some current tensions in cosmology.
That seems to be part of the argument, yes.
One more thing that jumped out, non-locality. Quantum entanglement suggests faster than light correlations. How does QGD handle that if time isn't physical and interactions are instantaneous?
QGD addresses apparent non-locality through the instantaneous nature of gravity propagating through its underlying preonic network. In QGD, reality is strictly causal, but gravitational influence is immediate.
So if you change something here, the gravitational effect on something far away is felt instantly.
That's the claim. A change affecting one particle instantly influences others gravitationally via this fundamental network. This has really interesting implications for Bell's theorem experiments.
How so?
QGD suggests that maybe the observed violations of Bell inequalities, which seem to rule out local realism, might not necessarily require quantum entanglement. Perhaps they could be explained by this kind of classical but instantaneous gravitational interaction. If both quantum entanglement and QGD's instantaneous gravity violate standard light-speed locality assumptions, finding ways to distinguish them experimentally becomes crucial.
So it offers a potential classical, albeit non-local in the standard sense, explanation for Bell correlations.
It seems to propose that possibility. It even goes further, suggesting that things like nuclear decay might potentially be triggered by distant astrophysical events due to this instantaneous gravitational influence.
Triggered nuclear decay from across the cosmos.
Wow, okay. Navigating scientific debate and evidence.
Mm-hmm.
This framework is just vast and so fundamentally different from standard physics. How do we even begin to evaluate something like this, especially when, like you said, sometimes it predicts the same outcome as established theories, but for totally different reasons?
Yeah, that's the challenge. And it brings us back to basic principles of scientific evaluation, like Occam's razor, and really thinking about standards of evidence. The source material actually touches on this quite a bit.
Occam's razor.
Yeah.
The simplest explanation wins, right? Fewer entities. Kind of, but the sources clarify it's really about making fewer unnecessary assumptions. It's not necessarily about which idea is easier to understand. A scientifically simple hypothesis is one that doesn't add extra bells and whistles, extra concepts, without strong justification.
Can you give an example?
The sources use a non-physics one. Your car won't start. You just tested the battery and alternator, they're fine. The simplest explanation isn't suddenly assuming your test equipment failed or that cosmic rays interfered. It's assuming the next most likely mechanical failure, using fewer new assumptions. They also distinguish simple complex number of interacting parts from straightforward complicated ease of understanding. QGD might seem complicated, but the claim would be its axiomatic basis is simpler.
So for QGD, the question isn't, is discrete space easy to grasp, but does starting with discrete space and matter require fewer fundamental, underived assumptions overall than starting with spacetime, quantum fields, etc.?
Exactly. It's about the parsimony of the axioms. And then you need evidence. The sources use the whole long, messy debate around the Diet-Hart hypothesis and statins as an example of how science actually works when evaluating complex claims with conflicting evidence.
Right. That section went into all the back and forth about cholesterol, whether statins really work as well as claimed versus side effects, how different groups rely on different types of evidence, like massive randomized controlled trials versus observational studies or anecdotes.
Yeah, and arguments over interpreting data, like relative risk reduction versus absolute risk.
Yeah.
And the huge challenge of separating correlation from actual causation.
Yeah.
Especially in complex systems like human health or diet over time.
Yeah.
Presenting that whole debate neutrally, as the sources do. It's not about taking sides on statins, but about illustrating the process. Scientists grappling with evidence, questioning assumptions, applying standards, even when there's disagreement. That whole process is what needs to be applied to QGD.
So how would you apply that critical evaluation process to QGD's claims? Give me a specific example.
Okay, take the preonic waves versus GR's gravitational waves. Both predict a signal at LIGO. But the standard of evidence required to confirm QGD's version isn't just seeing the signal, it's finding evidence that directly supports the proposed mechanism. Is there any evidence the detector mirrors experienced a direct momentum transfer of physical push consistent with QGD that cannot be explained by GR's space-time stretching?
So you need an observation that only QGD can explain, or that contradicts GR's explanation.
Precisely. Or consider the redshift claims. QGD says observed redshift is a mix of Doppler, interaction redshift, and intrinsic redshift. To evaluate that, you need observational methods that can somehow isolate or distinguish these different potential contributions. Can we find sources where QGD predicts significant intrinsic redshift, but standard models predict none? can we find evidence of the interaction redshift effect over distance. Just like the diet-hard debate needed ways to untangle diet from lifestyle factors, evaluating QGD needs ways to observationally untangle its proposed effects from standard ones.
So it's not enough for QGD to just match existing observations sometimes. It needs to do it with arguably fewer or more fundamental assumptions, Occam's razor.
Right.
It needs to explain some things better or resolve existing puzzles.
So successfully, yeah.
And critically, its unique specific predictions have to be confirmed by experiments or observations that can clearly distinguish them from the predictions of the theories it seeks to replace.
That's the gauntlet. That's the scientific method in action. Reproduce successes, explain phenomena more successfully or parsimoniously, and make new, testable, differentiating predictions. The ultimate judge, at the end of the day, is experiment and observation. Conclusion.
So we've taken a really deep dive into quantum geometry dynamics. It's a theory that takes this radical axiomatic approach, trying to build physics right from the ground up, starting with just discrete space and matter and deriving the laws from there rather than defining laws based on what we see.
Yeah, it offers this unified framework, but one that gives completely different physical reasons for familiar things: gravity, light, black holes, redshift. And it spits out a whole list of really distinct predictions.
Like repulsive gravity on large scales as an explanation for dark energy.
The non-existence of gravitational waves as actual space-time ripples.
Instantaneous gravity with all its implications for non-locality.
Invisible emissions from black holes, maybe even triggered nuclear decay from afar. It really forces you to question fundamental concepts we usually take for granted, like time being physical, or space being a continuum, or infinity existing in reality.
It definitely seems to meet the criteria of attempting to reproduce successes, and it certainly offers numerous specific, derived, testable predictions that are different from the standard model.
The absolutely critical challenge now is twofold. First, are its fundamental explanations judged by the scientific community as genuinely more successful? Maybe because they're derived from fewer axioms, or because they elegantly solve existing problems. And second, and most importantly, do those unique derived predictions actually hold up when put to rigorous experimental test? That's where the theory truly meets reality. Outro. So, we've seen how QGD paints this picture of a universe built on pure discreteness, where fundamental properties like momentum are intrinsic, interactions like gravity can be instantaneous across the cosmos, and even the rules of mathematics might be constrained by the physical world itself.
It certainly gives you, our listeners, something profound to think about, doesn't it? It asks us to question some of the absolute bedrock assumptions we have about space, time, motion, reality itself. Looking back at all this material we covered, what's the one thing that really stands out to you from this deep dive? Here's something to chew on. Consider QGD's core claim. Because physical reality is fundamentally discrete, the mathematics we use to describe it must also be fundamentally discrete. This implies concepts we use all the time in physics and math, like infinity, the continuum. Infinitesimals are just useful mathematical idealizations, convenient fictions, not actual features of physical reality. What are the truly deep implications for physics, for math, for our whole understanding of the cosmos if the universe is fundamentally, truly finite and countable at its core?